All right, everybody. Today, right now, it is 9 p.m., 8th of April. By, I will guess, 1 a.m. or 2 a.m. of 9th of April, I will finish this segmentary thing. Mark my words. Let's get it. So, let's revise what we have learned till now. I need the music. So, talking about what segmentary is all about. Segmentary is based on array thing. Like in array, we can use the prefix sum, right? Uh, in the similar way, we can use segment trees for range queries or interval queries, and like if the array given to us is like something like 3 comma 1 comma 2 comma 7 comma 5 comma 6, then by prefix sum this will be 3 4 and 6. 6 plus 7, that is 13, and it's 18. 18 and 6, that's 24, and adding a 3 at the end, 27, that's it. So this is a prefix sum thing. If we want to find the sum from index 2 to 4, we can do that by subtracting the prefix sum of 4, that is 8, that is 13, minus this. You can do that. So what segmentary is all about? Segmentary is a efficient data structure that allows efficient querying of interval and efficient updating of intervals. Range query related problems like summation, finding minimum, maximum, etc. is a thing. And segment tree has a thing like if this is one of the node, then this will have two nodes, and this will have two nodes, something like this. And let's say it's from L comma R. So mid will be and this would represent L2 mid. And this one would represent mid plus 1 till R. Alright. If the index of this is I, so this one would be 2i plus 1, and this one would be 2i plus 2. That all we know. And this one would be the base case sum at L. This point L would be equal to R. Similarly for these points. So this is what segment tree is seeming all about right now. And height of segment tree is log base 2n because of the 2 by 2 thing. Also height of left subtree minus the height of right subtree is equal to 1. This property is called balanced binary tree. And the segment tree looks like a binary tree. Each node has two childs. For all non-leaf nodes, leaf nodes represent a single element array. Leaf node is when L equals to R, and root node represents entire array. All right. Why to use segment tree? Like the prefix array thing would work well for finding the range sum query, like find sum for indexes in range 2 to 6. We can find that easily by prefix of 6 minus prefix of 2. but this prefix array thing fails for finding something like max. Like we can find max in range open bracket 2 to 6, and max in range 3 to 7 will be totally different. And leaf nodes and n-1 non-leaf internal nodes. Like this is the summation of the GP of the term. Like the bottom, let's say the suppose the array was of size 4, the bottom row of the tree will be representing the root nodes, and it will have n nodes. Above them it will be 2, then above that it will be 1, or something like that. But the 2n thing fails for the non-power of 2, so it's better to take 4n as the preferred size for segment tree. Now we already know that if this is representing I, this is representing 2i plus 1, this is representing 2i plus 2, and it will be from L to R, it will be from L to mid, it will be from mid plus 1 till R, and yeah, mid will be L plus R by 2. That's it. That we already know. Let's say if this value was 3, 1, 2, 7. So this is the base case. At the base case, we will have something like yeah. So this one would be the base case. At the base case, we will have something like L equals to R. Left pointer will be pointing towards the same thing as the right pointer. And these are the middle elements. The initial array was 3, 1, 2, 7. So while building the segment tree, these are all the leaf nodes, and these are the parent nodes, and this is the root node. Root node represents the entire array. This node represents the 2 points, 3 and 1, and this represents 2 and 7. So here we will fill up the summation to be 3 plus 1, that's 4. 2 plus 7, that's 9. And it will be 13. So this is how our segment tree will look like. So what happens is we will take an array zero, 1, 2, 3, 4, 5, 6, 7, and we will take some more. Let's put them at the back. This will be 0, 1, 2, 3, 4, 5. This one will be 6, 7, 8. 8 would be this one. This one would be 9. This one would be 10. Let's take 11. Let's take 12. And similarly, it will keep on going. So here the summation would be. So we will fill up with the base case. So the index of this would be 0, 0 and 1 and 2 and this is 0. 2i plus 1. 2 into 0 plus 1, that's 1. 2 into 0 plus 2, that's 2. 2 into 1 plus 1. 2 into 1 plus 1, that's 3. 2 into 1 plus 2, that's 4. 2 into 2 plus 2 into 2 plus 2. 2 into 2 plus 1, that's 5. 2 into 2 plus 2, that's 6. So here what we will fill up is we will come after it. So the base case will be hated by this one. So it is of index 3. And here we will put the exact 3 only. And this base case is at index 4. So at index 4 we will put straight up 1. Here we'll put 2. Here we'll put 7 exact. So the summation of these two will be put up here. That's 4. And summation of these two will be put up here. That is 9. So the 13 will be represented by this one. So this is our segment tree array that has been filled up. These are the dummy nodes we are taking up. This will be till 4n. So n is 4 here. So let's take it till 13, 14, 15, 16. So it will be till 16, let's say. But is this is the answer. So the main crux is, if this is I, this is 2i plus 1 and this is 2i plus 2. This represents from L to R, this represents from L to mid, and this represents from mid plus 1 to R. This is I, this is 2i plus 1, this is 2i plus 2. So now coming up to the code for the building tree. Build tree code. So build tree code is simple. First of all, we are using this entire segment tree class only. And yeah, this build tree takes index I for the root and L2R from where it is representing. So initially this will be representing 0 and this will be 0 and this will be n minus 1 to represent the entire array thing. And this is the base case. Base case was like these 4 nodes. At these 4 nodes, the L and R values were same. Like you can see L and R are same here. And if it's L and R are same, then what we are doing is we are filling the segment tree of I as array of L. Like you can see that segment tree of I, like this is the segment tree, and seg tree of 3 is same as the array of I. This is array of L. It is 3 or R. Similarly, we are calling up build tree for left and right. and we are doing this summation of the things. We are using a plus sign here because it is a range sum segment tree. We can use the min and max accordingly, if it's a minimum segment tree or the maximum segment tree. And here we are storing in the segment tree as the numerical value of the array in range minimum index query or range max index query like RMIQ. We can store the index here also. So this is the build tree code. So let's come and revise once again what we have learned. This thing, build tree. So build tree is based on ILR. This will be 0 0 and this will be n minus 1, and this is the base case. L equals to R. We have reached the leaf node. We are filling up the segment tree and we are returning. Next we are calculating the mid value, and we are calling up for the build tree for the left subtree and the right subtree, and we are filling up the value of the segment tree as from the child nodes, like this value and this value will and this value. So these two will sum up to give the value for this one, and these two will sum up for this one, and these two will sum up for the root. So that's the whole thing. That's the entire build tree code. Like the build tree code is simple. For ith node we had 2i plus 1 and 2i plus 2 as the left child and the right child, and I, this represents L to R. Mid is L bar R bar 2. This represents L to mid. This is from mid plus 1 to R. These are the leaf nodes. And what we are doing is we are first this I is 0, L is 0, and R is n minus 1. So mid will be n minus 1 by 2, and we are calling for L to mid this way, and mid plus 1 to R this way. Build tree, recursive calling, and again this will go and here comes the part when L and mid will coincide. So L and R are equal for this part. So that way, this is the base case hitting condition. So build tree code has been done. Build tree code has been done. Now next part comes to the update query, point update. Point update. So in the prefix array thing, when we will update the point, let's say if we will update this value as 3, then this will also become prefix sum value was 3, like this was 3. Let me write the prefix sum values for this. 3, 4 plus 2, that's 6, that is 13. And let's say if we update this value to be as 3, then this 4 will also get updated and it will become 7. This 6 will get updated and it will become 9. This 4 will become 6. This will become 8. and this 13 will become plus 2, that's 15. So it will update all the points beside it. So for one point update, we have to update all these n points. In the worst case, it would be n points that we have to update the values. So let's say we are point updating the value at q points. Let's say this point and this point, then q into n points we have to update. That is if we are using the prefix array, but we have to optimize it using the segment tree. Like segment tree, instead of doing it in big of n operation, it does it in n log n. So that is quite good of a saving for us. So let's say indexes was 0, 1, 2 and 3, and we are given at index 2. The value should be changed to 2. Let's say at index 1 instead of that, the value should become 2. So let's see how this change will propagate. So we know that this one is the 1 that has to be updated to 1 correspond. So what we are doing is we have to make it 2. So this one is the thing. So update segment tree works something like this. This represents the entire root, this represents the half, and this represents the right half. So we will ask for the index. Index is 1. This represents 0 till 3, and this represents 0 till 1, and this represents 2 till 3. So index 2, index 1 will lie in the right part, so we will move in the right part. Now we have reached here. This represents 0 to 1, like this was the 0th index, for an index 2 index 3 index, 0 to 1. So mid will be 0 plus 1 by 2, that's 0. So this will represent 0 till mid, so 0 to 0, and this will represent mid plus 1 to r, that's 0 plus 1 till 1, so that is 1. So we have found this one, so we have to update the value of this one. So we will update this, its value. We will update it and make it 2. When we will make it 2, the change will be corresponding here also, so it will become 5. And here we have to do no change. Only change was being done was in this case, because it was a point update and the point was lying in this coordinate. So we updated this and we reached here. So this became 5, so this will become 14. So that's it for the update case. What is happening is we have to find the index in the base cases where it is falling. Like this is the root, if it's falling in the left part or the right part. In the left part also we have to check if it is in the left of left or right of left. So it was falling here, so we updated here. So this is all the update tree code. Let's look at the update tree code template. So what this is doing is it is asking the index that which we have to update the current value to be replaced with a new value val. and this is the index we are currently at, and these are the L and R ranges of the interval. So what was happening is like we have to find the mid portion will be like this one, and this one will be left part, and this one will be the right part. If we found out that it lies in the left part, we have to update it there, or right part we have to update it there. So we found out mid. We find out that the index is less than mid, so this is probably left part, so we will update in the call recursively for the update in left part, and we will go for the right part if the index was besides of the middle part. This way what's happening is we will this condition will take us to the exact point at which we want to go and update that point update, and this one will be the base case. The base case will update the segment tree values to be as well, like at index it will become well, and at the end we are also propagating the update, like when this one was changed to 2, the next step was the summation of these 2 points for this, so automatically this will get updated, and as this one got updated and this stayed as it is, the change will be propagated upwards. So that is the update segment tree code. What it takes is it asks for the index at which we have to update with a new value well, and this is the index, and these are the range intervals, and at the base case it is updating it with a new value well, and it asks for the direction. It goes there and recursively calls for the update tree on the left or the right. So let's and one more thing, like the change can be propagated at max till the height of the array. Let's say at any point update we are updating it for any point only, like this point or this point or this point. So the change propagated here will maximum can go to here or here. So this entire thing will be the height of the segment tree. So the max height the change will get propagated will be the height of the tree, and yeah, so it's asking index and updating it as well, and base case is updating the value to be well. This is asking if it lies in the left subtree or the right subtree, and then it's propagating the change that has been done in the leaf node. Now let's come to the range sum query. So let's say we have array something like as 3 1 2 1 2, then we have 7, and 3 1 2 7 2 1 2 3. This is the array that is given to us. Let's write the index also. 0 1 2 3 5 6 7. So this is a size 8 array, and we are asked for the updating of the range sum from, let's say, index 2 till 6. So from here to here we have to find the summation 2 till 6. This part range sum query, like we can do it with the prefix sum of x minus something 6 minus 2. But that will take up a lot of time for number of queries, so we want to find, this will take up n big of n time for updating the values here and all these places, like the summing up. But we want log n approach, so we will use the range sum query. So what it does is it asks for the interval start and end. Start and end is needed. And this and this. There are 3 cases for that thing to happen. First case is out of bound. Second case is complete overlap. Third case is partial overlap. In the complete out of bound case, it will be something like this. Start is here, end is here, but the L and R thing is here. And another case would be this one. In this is the start case and the end case, but these values are lying here. This interval we are looking is lying here, but our interval that we have to query was here. The start and end is the interval we have to query for, and it's completely lying out of bounds. And this will be the complete overlap case. What's happening is this, we are looking in this interval start till end, but the current interval lies completely in the interval start till end that we are looking for. Remember, we are searching in the start till end, and our interval that we are looking for, we are currently seeing it is L2R. So it lies in that case. So that's a good case. And third case will be something like start will be here, and this will be here, end is here, and this will be here, or something like this L is here, start is here, R is here, and end is here. So this portion will come on. So we have seen that there can be three possible cases, and in three all of these three possible cases, like if it is out of bounds, then we will straight up return 0. Straight up returning 0. So this thing will eat up. Okay. So because it is completely out of bounds, and the complete overlapping case will return the entire segment tree of I, because this entire L2R, which is representing this segment tree of I in I, is lying in the region of our interest of start till end. And if it's a partial overlap, then what we do is we find the left part, and we sum it up with the right part. So coming at the code for the query thing, so this define query function, uh, this is the region start till end. These are the pointers in which we have to query, and this index is the current index of the portion or the interval we are looking at. This L and R are the range intervals of the interval that we are currently looking at, i.e., we are currently seeing it. So this one is the out of bounds case. Out of bound case is this start and end. You can see end is smaller than L. So that case would be one. And another case would be when R is lesser than starting of our interval that we are looking for. So we are looking for start till end, but this L2R lies here. So it is out of bound, we return 0. If it would have been a range maximum query thing, then it would return minus infinity. And if it would have been a range minimum query thing, then it would have been a plus infinity. Yeah, it's written here. Plus infinity for minimum segment tree and minus infinity for max segment tree. And if it's the complete overlap, like this portion, start till end lies in the region we are looking for, then this this portion, this interval L2R is represented by this. So we straight up return it. So we have returned it. Else the third condition would be partial overlap. For the partial overlap, what we do is we find the mid, and we call up for the query for the left part and the right part, and we sum it up. We sum it up because it's a some range sum query. If it would have been a range minimum query, then we would have taken a minimum. If it would have been a range maximum query, then we would have taken a max. So for the segment tree, we have defined everything. This was the build case. It's take I, L, and R. At the base case, when L is equal to R, we fill up the value. We fill up the value from the array from which we are building the segment tree, and then we just call this recursive function. This recursive function builds up the structure of the segment tree, and we fill the above nodes from the child nodes. For the update segment tree, it asks for the index, at what index, what value we want to update. And this is the pointers for the current interval we are seeing it. At the base case, it updates the value to be well, and to propagate the change, we find if that point update lies in the left part or the right part, if left of left or right of left, like this way, and then it propagates the change above. For the query, it takes the start and end, and these are the interval we are looking at. There can be three cases. This is out of bounds. Out of bound cases has been explained here. Our region of interest is start to end, but the region we are seeing through our eyes lies here. L2R lies here, but we want to look in the start till end. So we'll straight up return 0. And we will return plus infinity for the minimum segment tree and minus infinity for the maximum segment tree. And second case would be the complete overlap case. So when this portion completely lies inside the region we are looking at, and this L2R is represented by the segment tree of I, so we will straight up return it. And the third case will be the partial overlap. Partial overlap case, we will find the mid value and the summation through the left and summation through the right, and we'll sum it up and return. That's it. And we can do the min or max here also. So this has been the build tree, update tree, and the range sum query thing template. And calling for the build tree is this is I, L, and R. R is the entire array length, and start till end. This is the region we are querying for, and this is the root conditions, and this is the index at which we want to update the well. So there can be a lot of modifications also, like in the build tree and the update tree, when we are propagating or the building from the child nodes of 2i plus 1 or 2i plus 2, then we can take the min or max or anything here. And in the range sum query, in the merge step, in the merge step of yeah, I guess this range sum query merge step, segment tree of I, segment tree of 2i plus. Summation is plus, and we return 0. Range minimum, remove the query thing here. So in the minimum thing, we will take the minimum, and in the base case of the, we will return a positive infinity and a negative infinity here. So now looking at the define init child. In the define init child, it's simple. We have defined the segment T class, and we have defined the define in it. This will be self and array thing, and this array will be the array we are looking for, and will be the length of the array. Segment tree we have initialized with the length of 4n because of the dummy nodes thing, and we are calling for the build tree also. And in the build tree code, we have discussed a lot of times base case, fill it up with L or R, array of L or array of R, or maybe with the index if the range minimum index tree has been asked. And this will be the made. We are recursive calling for the self build tree of 2i plus 1 and L mid and 2i plus 2 bit plus 1 R to construct the hollow structure. And we are filling the hollow structure with calling for the child tips update at some index. We have to update. Well will be added in the base case only, and we will see if the midpoint lies is here or what. Then we will recursive call for that and define the query thing again. Query will be from start till end, ILR, and three cases will be there: out of bound case, complete overlap case, and partial overlap case. So in the in the complete overlap case, in the outer bound case, we will straight up return a zero because this portion is out of our region of interest of L and R. So it will not contribute anything and it will return zero. This L2R lies inside. So it will return the entire segment tree of I because L2R represents the segment tree of I. Partial overlap made, we will find the left portion and the right put, and then we will sum it up uh, for minimum segment tree. It will be maps and like this way. Now comes the lazy segment tree portion. I gotta work on this one. So the lazy segment tree has came again. For the lazy segment tree. Um, it's also called the lazy propagation. What we do is like updating values in a range. Earlier, what we were doing it was we used lazy propagation for the range update thing, not just the normal point update. The previous update segment tree code we have seen was for the point update, but this lazy segment for range update of points. Because if we will update a point to update point code, then the update point code was taking log n, and if we will update q such points, then it will take q log n. But we want something better for the range update thing to update the entire range in one go only. So we will use the lazy segment tree. So the propagation idea is like we maintain two arrays. Segment tree is the answer array, and lazy array is to store the updates that hasn't been reflected yet in the segment tree. Earlier we saw that it was taking new login time from the point update thing, but with lazy propagation we can do it in login time. And from q login to login, it's better in time complexity. So let's properly draw its diagram. Okay, should I copy it? I have to make it, I guess. Let's just draw the tree first. This will be a big tree. It will be fun to draw it. Yeah, yeah. So we will build it with the white color. So this one is the root node, and a it's too big. So this will be a size of 8. This segment tree will represent a size of 8 thing, and we can draw it something like this. Oh fuck. It's and I gotta do use 5. No, what the fuck was that? So our tree will look something like this. And similarly, these, let's use this pen only. This one, 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 and get out of here. All right, this will be the segment rate that we'll be looking up. We will use the white color. That's all right. Let's define the array also first. 3, 4, 2, 5, 3, 6, 3, 4. This is the array indexing 1, 2, 3, 6, 7. This is the array and this is the indexing. So let's first fill up the base nodes. This will straight up be 3, will straight up be 4. This will be 2, 5, 3, 6, 3, 4, 3, 6, 3, and 4. So for this segment tree, like this is the base case. L pointer and R pointer will be pointing the same. So this will sum up and give it to its parent node. So the sum that will come up here is this will be 7, and 2 plus 5, that is also 7, 9, 7. And this one also sum it up, 7, 7, 14, 9 and 7, that's 16, that's 30. So man, what's so this is the root, these are the parents, these are the child nodes, leaf nodes. And what's happening is we have to propagate the change. We have to propagate the change. So let's suppose from index 2 till 5, 2 till 5, we have to do a plus 2 everywhere. So this will become a 4. This will become, what will it become? 7, 5, and 8. This is the entire range in which we are updating. So this 2 to 5. This 2 to 5 is our region of interest, and this is van. So this is start, this is end, this is well. All right. And it represents. So what I'm doing is I'm gonna ILR thing 0, 0, n minus 1, that's 7. Y plus 1. This way it will go y plus 1 to y plus 2 and shits like this. So let's fill up the value of I for each of them. I'll use this pen. I is 0, 1, 2, 3, 4, 5, 6. This 5 is because of 2I plus 1. I is 2 here. 2 into 2 plus 1, that's 5. 2 into 2 plus 2, that's 6. So what will be here? 2 into 5 plus 1, that's 11. Let's see. This is 6, 7, 8, 9, 10, and that's 11. All right. It's 12, 13, and that's 14. Value of I. So what we have to do is we have to update propagator plus 2 change in the range 2 to 5. We have to do a plus 2 in this array. So 2 will become 4, 5 will become 7, 3 will become 5, 6 will become 8. So so going at the lazy tree code, this is the lazy tree code. This is the defining the lazy tree class. This build tree is exactly the same.
है आम खाएगा मतीरा खरबूजा आम मतीरा खरबूजा खाना है क्या तेरे को हैं
हाँ वो
अब मेरे को सब पता है तू क्या कर रहा है
क्या
मेरे
कर
से क्या छुपा रहा है
क्या कर
सब पता है मेरे को तू क्या करता है
क्या स्ट्रीमिंग?
हाँ वो
हाँ
ट्विच पे कर रहा है
ऑल राइट
मेरे को पता है बिगड़ा है बिगड़ा है सब पता है मेरे को
गेट अवे.
ये डाल रहा है स्क्रीन रिकॉर्ड कर करके डाल रहा है आवाज भी जाती है क्या ए पावला
इंग्लिश.
हाँ तो तभी तो बोला इंग्लिश में बोलूंगी तो समझ जाएंगे ना
So yeah, नहीं. So we have to increase the value by plus 2 for in the range to start till end from the index 2 till 5. So this 2 will become 4, 5 will become 7, 3 will become 5, and this will become 8. This is the entire thing I have done till now. I have to look into this. So this build tree code is exactly as it is. So we are not going to see that again. We have to see the update thing. What this update is doing is it's asking for the start till end portion in which we want to update value in this interval. So first of all, if it's the non-overlap case, like this L and R will represent some portion of the segment tree. If this is not in the region, let's say this was representing something, but we have to look into the segment tree of this region, then we will ignore the L and R portion. So the non-overlap case will just simply return. And if the complete overlap case is there, like the L and R portion lies completely inside, Let me write it properly. I use blue or what? Pink pen. All right. So this was 30. We will go down this way. We will go down this way. And this is representing index from 0 till 1. So this is not useful to us. So we will directly return. Now we will come here. This one is representing the index from, let me write it here also, 2 to 3, 4 to 5, 6 to 7, and this is 0 till 1, and this is 1, 2, 3, 4, and 5, 6, 7. What? Oh no, that was zero based. 0, 1, 2, 3. That is 4. That is 5. That is 6. That is 7. So this is zero based indexing, and 2i plus 1 is also this. So we are in the interested in the range of 2 to 5. So this is from 0 to 1. So this is a non-overlap case. So it will just simply return. And when we will come here, when we will come here, this lies in 2 to 5 range. So it has a two values. So what we'll do is we will do a +4. Let's use a green pen. It will give a +4 because it has two childs. So this +4 will be propagated, and this side will propagate a +4. Now, when we will be coming back to this side, this is representing from 4 till 7. This 4 and this 7, it representing is this. So we have to look in 2 to 5. So 4 and 5 lies in this portion. So it will come down here. 4 and 5 completely rise in this portion. And like 2 to 3 was in this portion. So +4. So from this side also we'll get a +4. And then we will go this way. This is from 6 to 7. But we are looking from 2 to 5 range of the interval. So this one will return nothing, just as it is. So from this portion, again, in total, we got a +4 here. So basically, here what we got is +8, and this will become 38 because the left subtree contributed a +4 from the 2 to 3 range, and the right subtree contributed a +4 for the 4 to 5 range, because what we was looking for was 2 to 5, and 2 to 3 and 4 to 5, that sums up to 2 to 5, and we are adding a +2 in all these values. So this will give it up. Earlier its sum was 30, Now it became 38. It's evident because at every point we have added a plus 2. So this is the thing. So what the thing is, we have to go down left and right. We have to check what this this node is representing, what interval this node is representing, and if this the represented interval lies in the interval that we want to look for, then we will do the contribution thing by the value into the number of nodes that are useful for us. So this way, this will contribute a plus 4, and similarly, this plus 4 will be contributed directly till the above. So plus 4 will be going till the top for the root node. And similarly, this plus 4 came up from the right subtree. So looking at the code, this is update range. That's update range, not the update point, not the point update. Earlier we have learned about the update point method, but this is the update range. This is the interval start till end, and this is the interval L to R that we are currently seeing at. If this, let's look at the non-overlap case. If this is a non-overlapping thing, this will straight up return like this 0 to 1 was non-overlapping with 2 to 5. So it straight up returned nothing this here. And complete overlap case is this one, like this 2 to 3 is in complete overlap with this 2 to 5 because 2 to 3 lies entirely inside the 2 to 5. So what happened is segment tree of I was increased plus equals R minus L plus 1 into val. R minus L plus 1 is the number of child nodes it have, and it got updated with the val thing. So segment tree of I will be updated by plus 2 into 2 nodes. So plus 4 will be updated. And if the child nodes are existing, we have to propagate it in the lazy array also. And then we'll return. And then looking at the partial update, partial overlap thing, it's same as the range sum query thing. Find the maid, go build the left subtree 2i plus 1 and the right subtree 2i plus 2 and add it up. And also pushing down through the lazy array. If the lazy array still has elements, then just multiply and add it and push it down to the left and the right child of the, like this one, left and the right child of the lazy array will be propagated in here also. So there is some understanding of this. I'm totally not able to explain this why we use this lazy array thing, but I can evidently see that the completely overlapping and the non-overlapping portion will contribute to the number of nodes into the value that has been updated. So now let's go to the RMIQ thing, the segment tree for storing the index thing. And RMIQ is derived from the RMQ only. Like it basically shows the index of the maximum element that we have seen so far. Like in query range from 1 to 4, from index 1 to 4, this one, the maximum value is 9. But instead of that, we are storing the index of 9. Index of 9 is 0, 1, and 2. So 2, we are storing that in the segment tree. What is range maximum index query? Instead of returning a value of the maximum element, we return the index where the maximum element occurs. All right. So this index was 2. So we returned a 2. So the key idea is, instead of storing the value of the segment tree, we store the index of where we have found the maximum value. So segment tree of I will store the index of the maximum element. During the merge step, we compare. Let's see. So this is the entire class code of the segment tree for the RMQ and RMIQ. There is a little bit of difference only in RMQ and RMIQ. In RMQ and RMIQ, like what we were doing is we were storing the values in the segment tree, but this time we are storing the index L. Earlier it was array of L in normal range max query thing, but we stored L in RMIQ because it's a index based thing. And what happens here is the build tree code is exactly the same as that of the RMQ. RMQ code is this one. Build tree is this. If we'll compare this one with RMIQ, it's exactly the same. Mid is there, and we are creating up the hollow structure of the left subtree and the right subtree of the 2i plus 1 and 2i plus 2. And the left index will be 2i plus 1. Right index will be 2i plus 2. The segment tree will store the max of left index and the right index, and t will be equal to lambda, like this way. This is entirely same meaning of the above thing. Like in above, we have used define the key equals lambda, such that lambda x will be the array of x. But in this one, that's if else condition. So the build tree is exactly the same, just such that instead of directly using segment tree as max of array of 2i plus 1 and array of 2i plus 2, we are storing the getting the indexes and storing the based on the index value. Also, the range query thing is also similar. Here also we have these start and end and L and R in segment tree and array for them. I don't need these here. I don't need these here. This is bullshit. I don't need it here also. In the build tree also, if it's there, let me remove it. That's done. The build tree code is exactly the same. In the query thing, non-overlap case, overlap case, three cases will be there. Out of bound, that means the non-overlap case. Complete overlap case, that means it lies entirely inside the region that we are searching for. Partial overlap means some portion lies inside and some portion lies outside. So in that way, when is no overlap, when will it will no overlap? No overlap will be when start and end is like this. This is n and this is L. End is less than L. That's right. Or when start is less than R. So this is R. This is start, and this is end. So this start and this R. So R is less than start thing. This is less than this. The start is less than R, so that will be no overlap thing. So in this case, earlier the range max query thing, we are returning minus infinity. But instead of minus infinity, because it's a range max index query, we are returning a minus one. And second case would be complete overlap case. Start, start and end lies here, but the region we are looking lies completely inside the start and end. So this will totally return the segment tree of I. And segment tree of I this time is storing the index only, but we will return it that way only because it's a range backs index query segment tree. Let me write it here also. And the seg tree of I stores the max Index only. That's right. Now looking at the partial overlap case. So the partial overlap case will have something like it will be something like this. These are the ranges. This is this. So this one is the overlapping portion, or maybe this is the thing and this is the thing. So this is the overlapping portion. So the overlapping portion will be counted up. We are getting a mid and we are finding the left and the right by calling for the query of that thing. And if any of them is invalid, return the one that is valid. Otherwise, return the whatever is. All right. So this one is also done. Non-overlap case, complete overlap case, partial overlap case, partial overlap case. We are getting the left and the right indexes, and we are removing the. If the left is invalid, then we are picking up the right. If the right is invalid, it's a -1, so we'll picking up the left. And otherwise, we are taking the one which is a higher array value because it's a max text thing. And looking at the update index value, so at some index we are using the update. At this index, do the update in the value to be done. This will be the new value, and this are our coordinates that we are looking for. And if it's a base case, then only we'll propagate the changes. And one more thing, this is stupid. I don't need this. Let me search it again also. I saw it somewhere previously. Okay, okay. I don't need it. Okay. Lazy segmentary code is this. And RMIQ, 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 RMIQ. We were on the update. Yeah. So base case leaf node, that's right. In the base case leaf node, we are storing the new index. Index and well. Yep. We are having this mid, calculating it as the left and the right pointer by 2. If this index that we are looking for lies less than mid, so that means it lies in the left subtree. Otherwise, it lies in the right subtree. Man, what is this Chinese language is here? Query. Why the fuck, man? Why are you showing me this Chinese language? Update at index. We have to update val. This is the base case leaf node. In leaf node, we are storing index only of the updated val. This mid will be calculated if the pointer lies in the less than mid. So we will call for the left subtree. Otherwise, tries in the right subtree. We will call for the update in the right. RMQ, what we used to do was range of segment tree of I. We will store it with as the max of this left child and the right child. But here we have to store the index. So left index would be the left child and the right index would be the right child. And we are storing based on the array of left index or right index because storing index. So that's it. That's it. We have learned the entire segment tree and it's 1 hour 43 minutes of streaming. So let me summarize it once again. First, we saw the segment tree, size, build query, and all this bullshit, recursion and depth. All this is bullshit. This should go down. Then we saw what the input array was given, and we are constructing a 4n. Then we are defining a build tree, ILR, base case. That's it. Left child plus right child. 4n, 4n. That's all. Then we saw the update 3 point update. नीचे वाले में चल गई पर चूंकि हो गया. Then we saw the point update. And we saw the range query. And we saw the init style. Quantum data inquiry has been done. Will tree with be
हेलो एवरीवन, वेलकम टू माय चैनल कोड स्टोरी विद माइक। तो आज हम सेगमेंट ट्री के कंसेप्ट क्वेश्चन खेलेगा। वीडियो में सेगमेंट है। ओके, थोड़ा सा स्टार्ट करते हैं। यू विल गेट द बेनिफिट ऑफ बीइंग कंसिस्टेंट। ठीक है, जब भी आपको कंसिस्टेंट बेनिफिट पता चलेगा, यू विल स्टे टू बी कंसिस्टेंट। ठीक है, आई विल लॉट ऑफ बेनिफिट्स इफ यू आर कंसिस्टेंट कंसिस्टेंट हार्ड बोल। ओके, ठीक है। तो आपको क्या करना है, सेगमेंट समझ गया, बिल्ड समझ गया। ठीक है, रेंज समझ गया। ये एक इंडेक्स को चेंज करता है, सेगमेंट को सेगमेंट का चीज अपडेट क्वेरी। तो आप ये बोलो पॉइंट अपडेट पॉइंट क्वेरी, है ना। फिर रेंज क्वेरी हमने सीख लिया था। उसके बाद हम 4 टाइम्स n साइज ऑफ एरे क्यूब लेते हैं, वो भी हमने सीख लिया था। और हमने दो क्वेश्चन भी बना लिया था, क्वेरी सम 2 एंड रेंज मिनिमम क्वेरी। ठीक है, तो आपको याद होगा अभी जस्ट मैंने आपको बताया कि वीडियो नंबर 2 में मैंने ये पढ़ा था, अपडेट क्वेरी मतलब किसी इंडेक्स को अगर आप चेंज कर दिया है, किसी एक इंडेक्स को उसकी वैल्यू अगर चेंज कर दी जाए तो सेगमेंट। ठीक है, और बहुत ही फेमस टॉपिक आज हम लोग पढ़ने वाले हैं। वीडियो नंबर 2 है ना, ये वाला कुछ बहुत हार्ड अचीव क्वेरी। रूट से स्टार्ट करते थे और रूट में मिड निकाल लेते थे। मिड अभी देखो तो मेरा कितना आ रहा है, मेरा मिड आएगा 0 + 7/2। और यहाँ पर 0,7 का मतलब क्या हुआ कि जो रूट है ना वो पूरे अरे को रिप्रेजेंट करता है, 0 से लेकर 7th इंडेक्स तक को रिप्रेजेंट करता है। हमने मिड इंडेक्स निकाला, क्या निकल कर आया, 3 आया। ठीक है, और जो जिस इंडेक्स को हमें अपडेट करना है वो 3 है। ठीक है, तो ऑब्वियस सी बात है जो इंडेक्स है वो लेस देन इक्वल टू मिड है ना, मतलब लेफ्ट साइड में ही वो इंडेक्स होगा। राइट, तो हम लेफ्ट साइड चले गए। यहाँ तक क्लियर। ओके, अब यहाँ पर जब आए हैं तो ऑब्वियसली हम यहाँ पर फिर से मिड निकालेंगे। मिड इज इक्वल टू 0 + 3/2 दैट इज 1, है ना। तो जो मिड हमारा निकला है और हमें जिस इंडेक्स में जाना है, हमें जाना किस में है, आईडीएक्स हमारा 3 है और मिड जो है हमारा 1 आया है। तो ऑब्वियस बात है यहाँ पर जो इंडेक्स है वो ग्रेटर देन मिड है, मतलब राइट साइड में हमें यहाँ से जाना पड़ेगा। तो हम यहाँ पर राइट साइड में आना। ठीक है, यहाँ पर मेरा मिड कितना आएगा, 2 + 3/2 कितना आ जाएगा, 2 आ जाएगा। और हमें जाना है इंडेक्स 3 पर जाना है, तो ऑब्वियसली हम राइट साइड में जाएंगे। तो राइट साइड पे गए, यहाँ पर अगर आप ध्यान दो जो एल है और जो आर है एक्जैक्टली बराबर है ना, और वो हमारे आईडीएक्स से बराबर है। राइट, तो हम इधर रुक जाएंगे, ऑब्वियसली यही मेरा टारगेट इंडेक्स था और यहाँ पर हम आएंगे ही कभी ना कभी। तो यहाँ पर हम आ चुके हैं। इसकी वैल्यू में क्या करनी थी, इसकी वैल्यू में 6 बनानी थी, तो हमने काट के क्या किया, इस वैल्यू 6 कर दी। ठीक है, अब सिंस इसकी वैल्यू हमने 6 करी है तो अब देखो रिकर्शन हमारा रिटर्न होगा इधर, ऑब्वियस बात है रिकर्शन हमारा यहाँ पर से रिटर्न हो जाएगा। तो अब यहाँ पर आप यार यहाँ से आपने कॉल किया था। ठीक है, रिकर्शन। अब आप वापस रिकर्शन से आ गए हो तो इस ये जो नोड है इसका लेफ्ट साइड का वैल्यू क्या है, 2 है और राइट साइड का वैल्यू देखो अपडेट हो चुका है, 6 हो चुका है। तो 2 + 6 8 हो जाएगा। तो ऑब्वियस बात है हमें इसको भी अपडेट करके 7 से 8 करना पड़ेगा इसको। यहाँ तक क्लियर। अब ये भी रिकर्शन उल्टा लौटेगा। मैं यहाँ पर पहुंचा, इसका लेफ्ट साइड का वैल्यू क्या है, 7, राइट साइड का वैल्यू 8 हो चुका है ना, तो 7 + 8 क्या हो जाएगा, ये 15 हो जाएगा। मैंने काट के इसको 15 कर दिया। अब वापस से मैं यहाँ लौटा। ठीक है, तो मैं अभी यहाँ पर आ चुका हूँ वापस से। इसका लेफ्ट साइड का वैल्यू 15 हो चुका है, राइट साइड का वैल्यू तो ऑलरेडी 16 है, तो 16 ही रह गया। 15 + 16 कितना हो जाएगा, 31, 31 हो जाएगा। ठीक है, तो 31 हो जाएगा। अब हमारे ओवरऑल ये सब पूरा एरे का सम देखो, ये रूट का वैल्यू जो है ये 0 से लेकर 7 को रिप्रेजेंट कर रहा है इंडेक्स को। तो ओवरऑल एरे का सम देखो 31 हो चुका होगा। अब यहाँ पर वेरीफाई भी कर सकते हो। यहाँ तक क्लियर है। ओके, तो अब बात आती है कि ये तो मैंने एक इंडेक्स को अपडेट मारा ना, तो यार एक इंडेक्स को अपडेट करने में कितना लगता था, log ऑफ n लगता था टाइम। राइट, अब हमारे पास अब रेंज आ चुका है, रेंज दिया रहेगा और उस रेंज में सारे इंडेक्स को हमें अपडेट करना पड़ेगा, रेंज अपडेट। तो मान लेते हैं प्रॉब्लम दिया रखा है कि स्टार्ट से लेकर एंड तक का इंडेक्स में जो इंडेक्स आ रहे हैं सब में सबकी वैल्यू को आपको चेंज करना है, या तो सबकी वैल्यू में +2 करना है एंड सो ऑन। तो आप हर एक इंडेक्स को में जा जाके उसकी वैल्यू को अपडेट करोगे तो उसमें प्रॉब्लम क्या होगी, हर एक अपडेट में लॉग टाइम लगता है और इस रेंज में कितने एलिमेंट हो जाएंगे, एंड माइनस स्टार्ट +1 इतने नंबर ऑफ एलिमेंट्स हो जाएंगे और वर्स्ट केस में वो n एलिमेंट्स होंगे। ठीक है, वर्स्ट केस में ऐसा भी हो सकता है ना, वो बोलेगा कि भाई सारे एलिमेंट्स 0 से लेकर 7 तक के सारे एलिमेंट्स में आप +2 कर दो या तो सबको सबकी वैल्यू को अपडेट कर दो। तो हर एक इंडेक्स को अपडेट करने में लॉग टाइम लगता है और सारे इंडेक्स को अपडेट करने में कितना टाइम लगेगा, n log n लग जाएगा। ठीक है, तो ये काफी महंगा ऑपरेशन है n log n, है ना। हम देखते हैं कि इसको फर्दर कैसे अपडेट किया जा सकता है ना। ठीक है, तो प्रॉब्लम तो समझते हैं कि क्या प्रॉब्लम है। तो अब देखते हैं कि रेंज अपडेट को ऑप्टिमली हम कैसे कर सकते हैं, है ना। ऊपर जो पॉइंट अपडेट था, पॉइंट अपडेट को लगा सकते हैं हर एक इंडेक्स में स्टार्ट से लेकर एंड तक में, बट उसमें क्या प्रॉब्लम होता है, n log n लग रहा था। बट देखते हैं कि यूजिंग द कंसेप्ट ऑफ लेजी प्रोपगेशन जो कि काफी फेमस टॉपिक है, हम कैसे इसको और अपडेट कर सकते हैं, लेजी प्रोपगेशन। ठीक है, ओके, देखिए मैं प्रॉब्लम देखा कि नम्स में इंटर कर दो, उसकी वैल्यू +2 कर दो, हमारा एग्जांपल ये लेंगे। ठीक है, हर इंडेक्स में +2 कर दो, तो देखते हैं हमारा सेगमेंट, ये मेरा मैंने सेगमेंट पहले बना दिया, सेगमेंट आपको ऑलरेडी आता रहना है। ठीक है, तो मान के चलते हैं पहला क्वेरी आपका था कि अपडेट रेंज आपको दे दिया है, बोला गया 2 से लेकर 5 तक के एलिमेंट में सब में +2 कर दो। मान के चलते हैं ये क्वेरी था आपका। ठीक है, इंडेक्स नंबर 2 से लेकर इंडेक्स नंबर 5 तक के सारे एलिमेंट्स में +2 कर दो, इसमें +2 कर दो, ये 4 बन जाएगा, ये 7 बन जाएगा, ये 5 बन जाएगा, ये 8 बन जाएगा। ठीक है, तो ये अपडेट करना, तो देखते हैं कि किस तरह हम लोग अपने सेगमेंटरी को अपडेट करेंगे। ठीक है, स्टार्ट करते हैं। यहाँ पर मैंने लिख दिया कि इंडेक्स नंबर 2 से लेकर इंडेक्स नंबर 5 तक के सारे एलिमेंट्स में +2 आपको करना है। तो देखते हैं कि हम अपने ये जो सेगमेंटरी इसको अपडेट कैसे करेंगे। ठीक है, तो अब स्टार्ट करते हैं और ऑब्वियस बात आपको ये पता होगा कि रूट से हम लोग हमेशा स्टार्ट करते हैं और रूट का जो हम लोग सेगमेंटरी का जो अरे होता है ना, याद होगा आपको, जो अरे होता है सेगमेंटरी का, उसमें इंडेक्स नंबर 0 किसको रिप्रेजेंट करता है, रूट को रिप्रेजेंट करता है। तो इसका इंडेक्स नंबर 0 होता था, इसका इंडेक्स नंबर 2i+1 2i+2 होता था। ये सब तो आपको बेसिक पता चल चुका ऑलरेडी, है ना, तो ये मैं दोबारा नहीं बताऊंगा। ओके, यहाँ से रूट से स्टार्ट करते हैं। तो अब एक चीज ध्यान दो, जो रूट है इसका इंडेक्स जो है वो 0 से 7 तक को रिप्रेजेंट कर रहा है, बट हमें तो इंडेक्स नंबर 2 से 5 तक को ढूंढना है ना। तो ऑब्वियस बात है हम लेफ्ट भी चले जाएंगे और राइट भी चले जाएंगे, क्योंकि कुछ इंडेक्स, क्योंकि देखो मुझे इंडेक्स नंबर 2 चाहिए, 3 चाहिए, 4 चाहिए, 5 चाहिए। कुछ इंडेक्स लेफ्ट साइड में होंगे, देखो इंडेक्स नंबर 2 यहाँ है, 3 यहाँ पर है, और कुछ इंडेक्स राइट साइड में होंगे, देखो इंडेक्स नंबर 4 यहाँ है, 5 यहाँ पर है। ठीक है, तो ऑब्वियस बात है मुझे 0 से ये मुझे 2 इंडेक्स
This side and this side. We will go this side, come this side, this.
इंडेक्स नंबर 5 तक का एलिमेंट चाहिए था, बट ये जो रूट है ना ये 0 से 7 तक रिप्रेजेंट कर रहा है। कुछ एक्स्ट्रा इंडिसेस भी हैं इसमें, है ना, तो वो हमें नहीं चाहिए। तो हम क्या करेंगे, लेफ्ट साइड और राइट साइड चले जाएंगे। तो सबसे पहले मैं लेफ्ट साइड जाके एक्सप्लोर करता हूँ। अभी मैं यहाँ पर आ चुका हूँ। ओके, ठीक है, अभी मैं यहाँ पर हूँ 14 के पास। तो अब देखो 14 का जो रेंज है, मतलब 14 जो है इंडेक्स नंबर 0 से लेकर इंडेक्स नंबर 3 तक रिप्रेजेंट कर रहा है, मतलब इसका L 0 है और R 3 है, बट हमें कौन से एलिमेंट चाहिए, इंडेक्स नंबर 2 से 5 तक का चाहिए। तो ये भी देखो ओवर, मतलब ये है, मतलब ओवरलैपिंग है। ठीक है, मतलब 0 से 3 को ये रिप्रेजेंट कर रहा है, बट हमें 2 से 5 चाहिए, तो देखो ओवरलैपिंग है। तो इस केस में भी हम फिर से स्प्लिट करेंगे, बोलेंगे भाई लेफ्ट भी चले जाएंगे और राइट भी चले जाएंगे। ओके, ठीक है, यहाँ तक तो क्लियर है। अब फिर से लेफ्ट चलते हैं, पहले यहाँ पर आ गए हम 7 के पास। ये किसको रिप्रेजेंट कर रहा है, इंडेक्स नंबर 0 से 1 को रिप्रेजेंट कर रहा है, जो कि मेरे रेंज से एकदम बाहर है, आउट ऑफ रेंज है ना, मेरे रेंज से बाहर। देखो रेंज में यहाँ पर 2,5 है ना, यहाँ पर तो 0,1 है, तो मुझे कुछ नहीं चाहिए मिलेगा यहाँ से, मैं यहाँ पर से रिटर्न हो जाता हूँ। ठीक है, मैं यहाँ से रिटर्न हो गया। ओके, यहाँ तक तो समझ में आ रहा होगा आपको। अब एक काम करते हैं, जब यहाँ पर आ गए तो अब राइट साइड में चलते हैं। यहाँ पर लेफ्ट साइड एक्सप्लोर कर लिया 14 का, तो यहाँ पर राइट साइड में चलते हैं। अब मैं 7 पर आया। अब 7 पर ध्यान देना, सबसे इंपॉर्टेंट पार्ट वीडियो का यही पर है, यहाँ पर पूरी तरह से ध्यान देना। अभी इस रेंज को देखो, 2 से 3 को रिप्रेजेंट कर रहा है और हमारा हमारा जो प्रॉब्लम है वो क्या बोला गया, इंडेक्स नंबर 2 से 5 तक के एलिमेंट्स को आपको अपडेट मारना है। तो देख लो 2 से 3 जो इंडेक्स है वो एक्जैक्टली हमारे रेंज के अंदर है। 2 से 3 जो है वो इस ओवरऑल रेंज के अंदर है, जो हमारा क्वेरी रेंज था ना 2 से 5 उसके एक्जैक्टली अंदर है 2 से 3। इसका मतलब क्या होगा कि इन दोनों में हमें +2 करना होगा, राइट, इन दोनों में हमें +2 करना होगा। तो यार एक बात बताओ, चलो +2 आप कर सकते हो, मतलब इसके लेफ्ट चले जाओ और इसमें +2 कर देना, इसके राइट चलो इसमें +2 कर देना। बट अभी ना आप उसको होल्ड में रख सकते हो। ऐसा क्यों, मैं आपको बता रहा हूँ, क्योंकि आपको तो अपडेट ही करना है ना, अभी आपको तो अपडेट करना है। तो आप एक काम करो, अगर मान लेते हैं यहाँ +2 जा कर देते, फिर वापस से जब आप यहाँ पर 7 पर आते तो इसका लेफ्ट साइड में कितना वैल्यू है, इसका तो 4 वैल्यू हो चुका है, 2 + 2 4 हो चुका है, और इसका राइट में 5 + 2 7 हो चुका है। तो अल्टीमेटली 7 अपडेट होकर क्या बन जाता है, 11 बन जाता है, 11। ओके, तो मैं क्या बोल रहा हूँ कि नीचे मत जा, तू इधर ही रुक जा, तुम नीचे मत जाओ, तुम रिकर्शन को यहीं पर रोक दो, ठीक है। और तुमको इतना तो पता है ना कि तुम्हारे नीचे में जितने एलिमेंट्स हैं वो तुम्हारे एक्जैक्टली रेंज के अंदर आने वाले हैं, इंडेक्स नंबर 2 से लेकर इंडेक्स नंबर 5 के अंदर ही आने वाले हैं। तो उन सारे एलिमेंट्स में +2 तो तुम करोगे ही करोगे, ये तो हमें पक्का पता है, क्योंकि इंडेक्स नंबर 2 से लेकर इंडेक्स नंबर 3 के एलिमेंट्स हैं यहाँ पर, जो कि हमारे 2 से लेकर 5 जो हमारा एक्चुअल क्वेश्चन था उसके रेंज के अंदर है। तो मतलब सारे एलिमेंट्स में आप +2 करने वाले हो, +2 मतलब ये जो वैल्यू आपको दे रखा है, ठीक है। तो नीचे मत जाओ, रिकर्शन को यही स्टॉप कर दो, और ये देख लो कि नीचे कितने एलिमेंट्स में आप +2 मारने वाले हो, इतना बता दो। कैसे निकालोगे, इसका एल आपको पता है, इसका आर आपको पता है, तो r - l + 1 कितना हो जाएगा, 3 - 2 + 1 दैट इज
R
a,
minus L
यानी कि
plus
दो
1
एलिमेंट्स में आप +2 करने वाले थे नीचे
plus
जाकर,
2 plus 2
नीचे
that's
जाकर दो
plus
एलिमेंट्स में
4.
+2 करने वाले थे, एक इसमें और एक इसमें। तो मैं बोल
So
रहा हूँ
this
मत
will
जाना अभी, क्यों जा रहे
contribute to
हो,
plus
आपको इतना
4
पता है ना कि
plus
दो
4
एलिमेंट्स में आप
will
+2
give
करने वाले थे, तो दो
plus
एलिमेंट्स में
4
आप +2 करोगे तो
will
कितना
give.
अपडेट आ जाएगा, कितना का बढ़ाता आ जाएगा, 2 एलिमेंट्स से, और सब में आप कितना वैल्यू अपडेट कर रहे हो, वैल्यू अपडेट कर दो, 2 * वैल यानी कि 2 * 2 दैट इज 4, यानी कि नीचे ना जाके यहीं पर डायरेक्ट 4 ऐड कर दो, तो ये 7 अब अपडेट को क्या बन जाएगा, 11 बन जाएगा, 11 बन जाएगा। यहाँ तक क्लियर है, ओके। तो देखो यहाँ पर आप लेजी हो गए, आप नीचे अभी नहीं जा रहे, फिर इसमें +2 करते, फिर इसमें +2 करते, वापस लौटते, फिर पता चल जाता कि हाँ भाई 11 हो चुका है आपका सम। तो नीचे क्यों जा रहे हो, इतना मेहनत क्यों करो, इधर ही से पता कर लो ना। आपको ये तो पता ही है कि नीचे के सारे एलिमेंट्स में अपडेट करना है आपको, क्योंकि वो आपके इंडेक्स नंबर 2 से लेकर इंडेक्स नंबर 3 के एलिमेंट्स हैं, जो कि हमारे एक्जैक्टली रेंज के अंदर है, ठीक है। तो मैंने अपडेट करके इधर ही आंसर निकाल लिया 11, और मैं इधर ही से रिटर्न हो गया कि भाई मेरा काम हो चुका है। बट रिटर्न होने से पहले, और ऐसा तो नहीं है ना, आपको इसको तो अपडेट करना ही पड़ेगा कभी ना कभी, इसको तो अपडेट करना ही पड़ेगा। तो पता है हम लोग क्या करते हैं ना, एक डमी ट्री बनाते हैं, जिसका नाम बहुत लोग लेजी ट्री भी रखते हैं, मतलब एक्जैक्ट एक और ट्री बनाते हैं। ट्री को हम अरे के फॉर्म में रिप्रेजेंट करते हैं, तो मैंने यहाँ पर अरे बना दिया। एक और ट्री रखते हैं जो सेगमेंट ट्री के साइज के बराबर ही होगा, उसका नाम हम लोग लेजी रख देते हैं, और उसमें अभी सारी वैल्यू 0 रखते हैं, एकदम इसका कॉपी होगा वो, साइज के मामले में साइज सेम होगा, बट इसमें स्टार्टिंग में सबकी वैल्यू 0 होगी, ठीक है। और वो डमी ट्री होगा, उसको लेजी ट्री भी बोलते हैं, कोई भी ट्री बोल सकते हो। तो पता ये हमें यहाँ से लौटने से पहले पता क्या करूँगा, उस लेजी ट्री में जैसे ये नोड अपडेट हुआ था ना, ये नोड अपडेट हुआ था, तो ये पता क्या करेगा, अपने इसका लेफ्ट और राइट चाइल्ड तो अवेलेबल है, राइट, तो पता क्या करेगा, लेफ्ट चाइल्ड में और राइट चाइल्ड में, लेकिन लेजी वाले ट्री में, लेफ्ट चाइल्ड और राइट चाइल्ड लेकिन लेजी वाले ट्री में बता देगा कि भाई देख तुम लोगों को ना फ्यूचर में अगर मैं तुम लोगों के पास आऊँ, अगर मुझे आना पड़ गया तुम लोगों के पास, अभी तो मैं नहीं आ रहा हूँ, मेरा रिकर्शन मैं नीचे गया ही नहीं, मैं तो उधर से लौट गया, अगर मुझे आना पड़ गया नीचे तुम लोगों के पास, तो मैं तुम लोगों से जरूर पूछूंगा, लेजी वाले ट्री से पूछूंगा कि क्या कोई वैल्यू है जो अपडेट करना बाकी रह गया, तो लेजी ट्री में मैं स्टोर कर दूंगा कि हाँ भाई 2 वैल्यू और 2 वैल्यू अपडेट करना था, जो कि हमने किया नहीं था इन दोनों नोट्स का एक्चुअली में, है ना, इन दोनों नोट्स का नहीं किया था, और हम ऊपर से ही लौट गए थे, क्योंकि नीचे आने के बजाय मैं ऊपर ही कैलकुलेट कर सकता था कि हाँ भाई इसकी वैल्यू 11 आने वाला है। तो इसने क्या किया, अपने लेफ्ट और राइट साइड में 2 और 2 स्टोर कर दिया कि भाई तुम लोगों को मैं कुछ वैल्यू स्टोर किया, फ्यूचर में अगर मुझे यहाँ आना भी पड़ा ना तो मैं अपडेट कर लूँगा इनकी वैल्यूज़ को, ठीक है। तो मैं जैसे इसका इंडेक्स टू ये इसका इंडेक्स क्या होगा, ऐसे करते हैं, देखो ध्यान दो, ये i = 0 है ना, इसका इंडेक्स क्या होगा 2i + 1 दैट इज 1, इसका इंडेक्स क्या होगा 2, ये 1 है ना, 2 × i + 2, तो यहाँ पर i 1 था ना, ठीक है, तो 2 × 2 + 2 4 हो जाएगा, इसका इंडेक्स 4 होगा, सेगमेंट ट्री वाले अरे का इंडेक्स निकाल रहा हूँ, ठीक है। और इसका इंडेक्स क्या हो जाएगा लेफ्ट वाले का 2 × i + 1, यानी कि इसका इंडेक्स 9 होगा, ठीक है। तो इंडेक्स नंबर 9 लेकिन लेजी ट्री में, मान लेते हैं इंडेक्स नंबर यहाँ पर मैंने 2 डाल दिया, ठीक है, और ये इंडेक्स नंबर 10 पर होगा, तो इंडेक्स नंबर 10 पर यहाँ पर मैंने 2 डाल दिया, लेकिन जो ओरिजिनल ट्री है, जो ओरिजिनल ट्री था मेरा, ओरिजिनल सेगमेंट ट्री अरे था, वहाँ पर देखो तो क्या प्रेजेंट था, यहाँ पर 2 प्रेजेंट था, और यहाँ पर 5 प्रेजेंट था, तो यहाँ पर ऑलरेडी वही का वही रह गया अभी 2 और 5, क्योंकि मैंने अभी तक इसको अपडेट ही नहीं किया है ना, मैंने अभी तक इसको अपडेट नहीं किया, राइट, इंडेक्स नंबर 9 और 10 में। लेकिन मैंने लेजी ट्री वाले में वैल्यू डाल के रख दिया कि अगर मुझे आना कभी पड़ा तो मैं देख लूँगा कि यहाँ पर 2 2 बचा हुआ है, कि हाँ बचा हुआ है, तो मैं अपडेट कर दूंगा, ये 2 वैल्यू उठाऊंगा और इसमें ऐड कर दूंगा, 2 इसमें और 2 इसमें, ठीक है। तो अभी मैंने क्या किया, यहाँ पर 2 और 2 स्टोर कर रख दिया, बट मैं यहाँ से रिटर्न हो जा रहा हूँ अभी, ठीक है, रिटर्न हो जा रहा हूँ, क्योंकि मुझे इसका वैल्यू तो मिल गया ना, 11 है इसका वैल्यू, ठीक है, ओके, यहाँ तक तो समझ में आ रहा होगा। अब देखो, अब आप यहाँ पर आए, जब 14 के पास आए, तो अब 14 देखेगा कि मेरे लेफ्ट चाइल्ड की वैल्यू क्या है 7 है, और मेरे राइट चाइल्ड की वैल्यू क्या है 11 है ना, देखो 11 हो चुका है, ये हमने अपडेट कर दिया था, तो 11 7 क्या हो जाएगा 18 हो जाएगा, तो हम लोग इसको अपडेट करके यहाँ 18 लिख देते हैं, यहाँ तक क्लियर है। अब मेरा रिकर्शन वापस से यहाँ पर लौटेगा, ठीक है, और अभी देखो इसका राइट रिकर्शन बचा है, अभी राइट रिकर्शन यहाँ पर आ गया, ओके। अब देखो ध्यान देना, राइट रिकर्शन हम लोग यहाँ पर आ गए, अब देखते हैं क्या होगा, ये इंडेक्स नंबर 4 से 7 है ना, इंडेक्स नंबर 4 से 7 है, ये वाला देखो ओवरलैपिंग है, तो हमें फिर से स्प्लिट करना पड़ेगा, कुछ इंडेक्स लेफ्ट साइड में होगा, कुछ इंडेक्स राइट साइड में होगा, ठीक है। अब देखो ध्यान दो, राइट साइड वाले को ध्यान देते हैं, ये 6 से 7 को रिप्रेजेंट कर रहा है, इंडेक्स नंबर 6 से 7, तो 6 से 7 तो मेरा आउट ऑफ बाउंड है ना, ये रहा, मुझे तो 2 से 5 का चाहिए ना, ये 6 से 7 में आउट ऑफ बाउंड है, तो मैं इधर से रिटर्न हो जाऊंगा, कुछ नहीं करूंगा, वापस आ दो, ठीक है।
I will continue it after. I'm tired. Okay. I'm gonna end the stream.